In the winter of 1879, when hard rock mining in the American West had already developed a strong professional orthodoxy, ventilation was considered a solved problem. Mechanical air pumps, furnace drafts, or mule-driven bellows were accepted practice. The accumulation of methane, black damp, and carbon dioxide in deep shafts was widely understood to be inevitable without forced airflow. It was in this context that Elspeth MacLeod, a Scottish widow newly arrived from Scotland by way of Kansas, quietly proposed a different method at a silver claim outside Leadville in Colorado. She suggested ventilating the mine without mechanical fans at all. Among experienced engineers, the response was swift and confident. Heinrich Vogel, a visiting metallurgist trained at the Freiberg Mining Academy, stated plainly during a site meeting in February 1879 that buoyant airflow alone cannot sustain adequate exchange in a horizontal drift exceeding 60 yards. His conclusion rested on accepted German mine safety calculations, which assumed minimal temperature differentials underground. Edward Hallam, formerly affiliated with the Royal School of Mines, London, and then consulting for investors in the United States, echoed the skepticism. He noted that chimney ventilation required vertical height and stable temperature gradients, conditions he believed inconsistent with alpine mines subject to rapid weather changes. Closer to home, Professor Nathaniel Briggs of the Colorado School of Mines dismissed the proposal more gently, but no less firmly. In a March 1879 letter to the Regional Investors Committee, he wrote that natural draft, though occasionally supplementary, cannot replace mechanical circulation in metallic loads of significant depth. None of these men regarded themselves as dismissive. Their objections were technical, measured, and aligned with prevailing engineering literature. To them, Elspeth MacLeod's suggestion appeared less innovation than misunderstanding. She listened without rebuttal. She simply asked for permission to demonstrate the principle on a smaller auxiliary tunnel. The mine had recorded 3 incidents of gas accumulation the previous year. One had rendered 2 workers unconscious for several hours. Another had forced a week-long shutdown, costing investors an estimated $4,300, a considerable sum for the period. Mechanical fans were on order from St. Louis, but delayed by rail congestion. If Elspeth MacLeod's idea failed, investors risked further closures. Workers risked exposure to lethal gases, and for Elspeth MacLeod herself, failure carried additional consequences. She had purchased a minor share in the claim with savings from her late husband's shipyard estate. A failed demonstration could eliminate both her financial security and her credibility in a community already uncertain about her unconventional presence. Social isolation compounded the technical risk. Mining towns of the era rarely accepted external authority without credentials. Elspeth MacLeod possessed no formal engineering certificate. Her experience came indirectly. Years spent assisting her husband in calculating shipyard ventilation stacks for steam vessels. That background, though practical, did not translate neatly into mining culture. Yet she proceeded without confrontation. She did not challenge established theory publicly. She simply requested a modest experimental drift, 90 feet in length, 8 feet high, 6 feet wide, branching from the main shaft. Most observers assumed the demonstration would quietly fail, confirming existing practice. Preparations for installing mechanical fans continued simultaneously, a precaution that underscored the community's expectation of inevitable disappointment. Work began on April 3rd, 1879. Elspeth MacLeod's first action was not excavation but measurement. She recorded ambient air temperatures above ground at 3-hour intervals for 10 consecutive days. The mean afternoon temperature measured 61 degrees Fahrenheit. Pre-dawn averages hovered near 34 degrees Fahrenheit. She also measured subterranean rock temperature within the existing shaft, which stabilized at approximately 49 degrees Fahrenheit year-round. These data informed her design. Instead of a straight auxiliary tunnel, she specified a gently ascending drift, angled upward at roughly 3.5 degrees toward a vertical exhaust chimney bored to surface level. The chimney diameter, 42 inches. Height, 68 feet from drift intersection to exit. Timber lining was deliberately avoided except its structural supports. Bare rock, she noted in her ledger, provided better thermal inertia. By May 10th, masons had begun shaping the chimney throat with locally quarried limestone. Mortar composition included higher lime content than usual, producing lighter coloration. Observers assumed this cosmetic preference until she clarified that lighter stone reflected more solar radiation at the chimney mouth, stabilizing temperature gradients. Progress remained steady. No speeches, no demonstrations, simply measurements entered in a leather-bound notebook, air velocity readings using smoke candles, humidity estimates via condensation observation, and periodic carbon dioxide tests using lime water precipitation, a common 19th-century method. Skepticism did not diminish. If anything, the absence of dramatic claims reinforced the assumption that the project lacked conviction. By early July, the chimney reached the surface. Elspeth installed a simple copper cowl, angled southwest to capture prevailing winds, while preventing downdrafts. The cost ledger recorded total expenditures of $612.74, roughly one-fifth the projected price of imported mechanical fans. Still, most professionals anticipated negligible airflow. Elspeth's understanding rested on a principle older than industrial mining, the stack effect. Warm air rises because its density decreases relative to cooler air. Even small temperature differences can generate measurable airflow when vertical height is sufficient. This principle had guided Roman bathhouse hypocausts, medieval castle chimneys, and ship ventilation funnels long before industrial fans existed. What contemporary mining engineers often overlooked was the consistent subterranean temperature of deep rock. In alpine regions, surface air fluctuates widely, but underground strata remain comparatively stable. Elspeth calculated that when afternoon surface air exceeded the mine's internal temperature by approximately 12 degrees Fahrenheit, buoyant flow would reverse downward through intake shafts, while cooler, subterranean air rose through the chimney. During cold nights, the gradient reversed again, sustaining continuous circulation. Her measurements suggested average airflow velocities between 90 and 140 feet per minute, modest but adequate for diluting methane concentrations below hazardous thresholds in a drift of the specified volume. She also exploited solar heating. The limestone chimney collar, lighter in color but thermally conductive, absorbed sunlight during daylight hours. This created localized warming at the chimney exit, enhancing upward draft even when ambient temperature differences were minimal. Historical precedents existed. North African desert dwellings used windcatcher towers. Persian Kianat ventilation shafts exploited similar principles. Naval architects in the 18th century had used chimney drafts to clear coal gas from holds. None of these practices were experimental. They were simply outside the immediate professional memory of Western mining engineers in 1879. Elspeth MacLeod did not claim novelty. She described the system as an application of familiar physics to unfamiliar terrain. On August 14, 1879, a late summer cold front moved through central Colorado. Surface temperatures dropped from 72 degrees Fahrenheit to 31 degrees Fahrenheit within 36 hours. Barometric pressure shifted rapidly. Several nearby mines relying on furnace ventilation reported smoke backflow and temporary gas accumulation. The auxiliary drift ventilated by Elspeth's system became an unintended comparative experiment. Foreman logs recorded methane readings in adjacent conventionally ventilated shafts, reaching estimated concentrations of 2.4%, below explosive limits but high enough to halt operations. Workers were withdrawn for 2 days. In MacLeod's drift, lime water precipitation tests suggested carbon dioxide levels remained below 0.6%. Smoke candle observations indicated continuous airflow despite external weather reversal. Average measured velocity, 118 feet per minute. No shutdown occurred. Fuel consumption also provided indirect data. Furnace-ventilated shafts burned roughly 1.8 tons of coal during the weather event. MacLeod's system consumed none. The difference, though initially anecdotal, attracted broader attention. Professor Briggs, previously skeptical, returned with calibrated thermometers and a recently imported anemometer. His September 1879 report documented a stable temperature gradient of 9 to 15 degrees Fahrenheit between the mine interior and chimney exit during daylight hours. Airflow averaged 112 feet per minute over a 72-hour observation period. The findings appeared in the October issue of the American Journal of Mining Engineering. The article avoided personal praise. It focused instead on quantifiable outcomes. Estimated 37% reduction in airborne carbon dioxide relative to adjacent shafts, elimination of furnace fuel costs during the study period, construction expenses recouped within 4 months through uninterrupted operation. Medical notes from the camp physician recorded fewer headaches and dizziness complaints among workers assigned to the ventilated drift, though causation remained cautiously stated. Investors, attentive to ledgers rather than theory, began requesting cost projections for replication. Heinrich Vogel revisited the site in November 1879. His second assessment, preserved in German correspondence, acknowledged that temperature constancy of deep strata was insufficiently weighted in prior calculations. He conducted independent smoke tests, confirming persistent airflow even under low solar conditions. Edward Hallam approached the issue analytically. He recalculated expected draft using British chimney formulas adapted for maritime ventilation. His revised memorandum concluded that Elspeth MacLeod's dimensions produced theoretical airflow closely matching measured values. Professor Briggs's final report adopted notably restrained language. He wrote that earlier assumptions underestimated the capacity of passive ventilation, where vertical geometry and thermal differentials are carefully integrated. None described the outcome as revolutionary. They described it as instructive. That shift from dismissal to analysis marked the true reversal. Replication began gradually in 1880. 3 additional Colorado mines installed similar ventilation chimneys within 12 months. By 1884, trade circulars estimated that 14% of mid-altitude silver mines in the region employed some form of passive stack ventilation, either as primary or supplementary airflow. Costs proved decisive. Average installation expense ranged between $500 and $900, compared with $2,800 to $4,000 for imported mechanical fan systems. Maintenance costs were minimal. Kansas investors, familiar with Elspeth from her earlier residence there, financed 2 retrofits in zinc mines near the state border. Reports indicated fuel savings equivalent to approximately 1.2 tons of coal per week during peak operation. Technical manuals began incorporating the method. Some credited Scottish shipyard principles. Others referenced anonymous Colorado field data. Attribution varied, but adoption widened. By the early 1890s, passive ventilation appeared routinely in mining engineering handbooks, usually recommended for moderate depth operations where temperature gradients remained predictable. The approach did not eliminate mechanical ventilation. Deep industrial mines eventually required forced airflow due to scale and complexity, yet passive systems persisted as cost-effective supplements. In 1910, the U.S. Bureau of Mines published Bulletin No. 45, which included comparative studies of natural versus mechanical ventilation in western silver mines. Several case studies traced lineage back to designs first implemented in 1879. Later, thermal modeling confirmed the physics Elspeth MacLeod had relied upon intuitively. Modern computational fluid dynamics simulations show that vertical shafts as short as 20 meters can sustain airflow exceeding 0.5 meters per second, given temperature differences of 8 to 12 degrees Celsius, values consistent with her recorded measurements. Some original chimneys survived into the mid-20th century. Field surveys in the 1940s documented intact masonry stacks, still producing measurable airflow decades after initial construction. Today, sustainable architecture revisits similar principles under different terminology: passive ventilation, solar chimneys, stack effect cooling. Contemporary environmental design literature frequently cites historical mining examples as early demonstrations of low-energy airflow management. The knowledge never vanished. It simply cycled through periods of attention and neglect. The episode illustrates a recurring pattern in technical history. Expertise often accumulates around prevailing tools, in this case mechanical fans and furnaces. Over time, familiarity with those tools can narrow perception of alternatives, grounded in older or cross-disciplinary knowledge. Elspeth MacLeod did not overturn physics. She applied it consistently. The surrounding experts did not lack intelligence or diligence. Their assumptions were reasonable within the framework they used. Nature, however, operates independently of professional consensus. Air density, temperature gradients, and buoyancy forces remain constant, whether recognized or ignored. When designs align with those forces, performance follows predictably. When they do not, no amount of professional agreement alters the outcome. Historical progress, therefore, often involves less discovery than rediscovery, the patient reapplication of principles once understood in different contexts.